All right, so we're going to start with exponential growth. When we look at exponential growth, what am I looking for to determine whether or not it's growth? So far, what have we said? Yep. So the B term has had to be greater than 1. Okay? So exponential growth, our graph is growing, so it's growing away. It's increasing. And with everything we've had to do so far, B has had to be greater than 1 to be exponential growth. But what we haven't done is talk about what that B is made up of. So our B is found by taking and saying 1 plus whatever the growth rate is. That's how we find B. So whenever we look at an exponential growth formula, we are going to use that definition of B in the equation. So we're going to have y is equal to A times 1 plus R to the power of T. So in this, okay, A still means the same thing. That is our initial value. The R is our growth rate. And T is the time over which it's occurring, okay? So all we're doing is instead of us having an X right there, we use a T. And then instead of using B, we use the definition of B, which is 1 plus our growth rate. So this is the formula we can use for any exponential growth question. So what we're going to do is we're going to read through the whole question and we're going to find the key parts, okay? So the original value of an investment is $1,400, okay? And the value increases by 9% each year. If it's saying increases, that automatically tells us growth, okay? Then it says use an exponential growth function to find the value of the investment after 25 years. So in this question, what is our initial value? What's our A? 1,400. What is our growth rate? 9%. Now, I'm not going to write it as a percent. I need to write it as a decimal. So how do I write 9%? Okay. Now we're going to write our years over which it's occurring, or our time, which is 25. And then we just set up our equation using those values. So we're going to do y is equal to 1,400 times 1 plus 0.09 to the power of 25. Once we have this set up, all I need you to do is type it in your calculator, okay? Well, this is talking about money. So how many decimal places do we have to have for money? 2.
When we write it, do we write it the same way we were writing it yesterday in the calculator? Like that y equals thing?
You don't have to do that for these, just because these were evaluating, not graphing. Those you only have to do for graphing. So when we type in, we just type it in exactly like it appears. So what do we get when we do that? Okay, so 12,072.31. Okay, and this is money, so we can put a money sign in front. Okay. Now, so that is, the investment is worth $12,000 if it increases by 9% each year after 25 years. Yes. Yes. Okay. Now, we're going to do 11 together, too. So let's go ahead and skip down to number 11. So number 11 says the number of student athletes at a local high school is 300 and is increasing at a rate of 8% each year. Use an exponential function to find the number of student athletes after 5 years. So the word increasing tells us it is growth. Okay. Now, what is our A? What is our initial value? Okay. What is our rate? What is our T? So we are good to plug everything in. We get y is equal to 300 times 1 plus 0.08 to the power of 5. And it will always be plus for growth functions. For exponential growth, it is plus. So we get y equals what? Okay, so we are talking about student athletes. Can I have 0.80 of a person?
No.
So what would I need to say for that? 441 student athletes. Yes, they did have a very, very strong debate today.
I was locked in. I wasn't even saying anything. I was like,
Yeah, yep. Third period did it too. It was just back to back, yeah. But these right here, that squiggly equal sign, that just means approximately. And that's showing that we're having to round it a lot because we're going to people, okay? So if it is talking about people or objects that you cannot have 0.80 of, that's when you round it all. You use the ceiling function, if you remember what that is, where you round up always. Yep. All right, now we're going to look at question 13. So for question 13, the population of a small town is 1,600 and is increasing at a rate of 3% per year. Use an exponential function to find the population of the town after 10 years. So what is RA? 1,600. What is our rate? Yep. Then what is our T? So we need to set that up. We're going to do y is equal to 1,600 times 1 plus or minus? Plus 0.03 to the power of 10. And what is that? It is what? Okay. Now, what are we talking about in this question? People. So that needs to be changed to? So 2,151 people. All right, I want y'all to do number 10 and 12 on your own real quick. The letters do spell art. So you have to find art first before you can grow through decay.
oh.
All right, what did y'all get for the answer to number 10?
15,149. So it's a change.
So 15,149 point, and that is money. Yep. So $15,149.72. All right, now for number 15, or not 15, number 12. What is your answer for number 12?
22,554.04.
Okay, it's what?
It's 200. 200,000. 25,540.
Yep. $225,543.04. Okay? We are going to work on saying it right. Just because it's a good skill to have. Okay? Now, we're going to go ahead and we're going to look at exponential decay now. Okay? So when we look at exponential decay, okay, that is where we start big and it's going to decrease over time. Okay? Now, everything we've looked at for decay so far, we've had B is less than 1. So what we're doing when we're finding our B here is we're saying 1 minus that rate of decay. Okay? So the equation for this one, we have y is equal to A times 1 minus R to the power of t. It's the exact same equation that we used for growth, except instead of adding, we are having to subtract. So A is still our initial value. R is our decay rate. And T is still our time. Okay, so the only thing difference is that we're subtracting whenever we have exponential decay. So just like when we're looking at exponential growth, there are going to be some words that are dead giveaways that we're looking at decay. Okay, so if we look at number 14, the population of a town is decreasing at a rate of 1%. So automatically when I see the word decreasing, I need to know decay. Okay, and it says in 2000, there are 1,300 people. Use an exponential function to find the population in 2008. So first, what is our initial value? Okay, what is our rate? 0.01. And what is our time? 8 years. Okay, it won't always give us the exact number. Sometimes we have to find it. The difference between 2000 and 2008 is 8 years. Then we just set it up. So y is equal to 1,300 times 1 minus 0.01 to the power of 8. So the exact same setup, we just change it from plus to minus when we go to decay. And so what is y going to be? But what are we talking about here? People. So what's the actual answer need to be? 1,200 people. Okay, then we're going to skip to number 16. Number 16 is probably one of the most regular uses of exponential decay. And it is depreciation. Okay, so a farmer buys a tractor for $50,000. If the tractor depreciates 10% per year, use an exponential function to find the value of the tractor in 7 years. Okay, so the word depreciation is our giveaway here that it is decay. If it's decrease, depreciation, decay. Okay, so what is our initial value? Yep, 50,000 for question 16. Yeah, for 16. Okay. Then for our rate, what is our rate? 0.1 or 0.10. You could do either. It does not matter. They mean the same thing. Okay. Now, what is the time for this question? 7 years. So we set it up. Y is equal to 50,000 times 1 minus 0.1 to the power of 7, which gives us what? 900 and what? Point. All right, and that is money. So that is $23,914.85. So after 7 years, that value has depreciated quite a bit, right? Now, for number 17, or not 17, you're going to do 17 on your own in just a second. We're going to do question 18 together. So we have the population of a town is decreasing at a rate of 2.5% per year. The population in 2000 is 28,000. What is the expected population in 2015 if this rate of decrease continues? So what is our initial amount? 28,000. What is our rate for this one?
0.025.
Okay. What is our T? 15. Okay, because 2000 to 2015 is 15 years. So we set it up. Y is equal to 28,000 times 1 minus 0.025 to the power of 15. And we get what is Y? 150. Oh, because that's already been rounded.
Yeah, when it's at
Okay. So it's 1,190. Yeah, 19,153 people. Okay, perfect. I want y'all to go ahead and do 15 and 17. So find A, R, and T, set up the equation, and plug it in. Did someone toot? Not again.
Literally had a whole talk about just go outside. Why would you do that? So now.
Good gracious. So it wasn't you today, Caden?
It wasn't me.
Then who was it? Who tooted in here?
Definitely not. Absolutely no smell. That smells beautiful and clean. Smells better than what's just in there. The desk is not far, so blame it on the desk.
I was wondering what that was. Sorry, I was like deeply staring into it.
Yeah, luckily it's white, it's like this.
All right. Okay, so for question 15, what did y'all get for the answer for question 15?
2 cents.
It is 2 cents.
Give me your 2 cents.
Yeah, she can't do that anymore.
All right, now, what about for 17? There we go.
Oh my god.
All right. So what we are going to do is I'm about to pass out our assignment, okay? And it has a front and a back. It is, the front is graphing. The back is this, okay? So we're going to talk about both halves of it. We're going to do a little bit of talking about both, and then I will let you work for the rest of class. I'm really sad because I have a yellow lanyard, I have a pink lanyard, I have a green lanyard, and I ordered more lanyards. And there's a blue one. I got a blue one, a white one, and a red one. No, I don't.
They're talking to me all.
I just like what they have.
I like really well.
They're cute. It's fun.
Everybody else?
This is one of the stretch ones. The inside ones are the ones that break.
I've either like hit my arm in there, like they come up and like smack me in the face.
I've done that before, yeah. It doesn't do bad, but it's slow. But
Yeah, but like,
Girl, I've been dating it.
Where do you read? Because she definitely would have had 0 in her mind. You're probably
Yeah, you just like.
I didn't believe that. 49.
She was like, hey, I want to also say Kaden. He's not doing it.
What?
No, he smelled it like that. Everybody else.
I'm telling you, you probably like said
He said, do something.
yeah, like.
All right. Okay, everybody. Okay, thank you. So, okay. Okay, we're going to start with looking real fast at our graphing functions one. Okay, so a quick recap of this. We look at our B term, which is the part that's being raised to the power of X to figure out if it's growth or decay. So for number 1, what is B?
Oh, wait, 4.
4, because that's what's being raised to the power of X. So is 4 greater than 1 or less than 1? So that means it's growth or decay? Growth. Okay. Now, is anything being added or subtracted to the end of it? No. So that means our asymptote is y equals 0. All right. Then you can just put that equation into your calculator, get the table, and I'm going to go over the third one with y'all just to make sure we've got it. For number 2, though, what is our B for number 2?
It's 1/2.
1/2. Is that going to be growth or decay? Okay. Now, this one has plus 2 added to it. What does that make the asymptote? So y equals 2. Okay. And so that means at y equals 2, what can you not do to an asymptote? Touch it, cross it, nothing. Okay. Now, we are going to do number 3 all together. Okay. So for number 3, what is our B? 1/3. Okay. So is that going to be growth or decay? Decay. Okay. Now, what is the asymptote going to be for this one? Yep. Y equals -1. So that means the asymptote is at -1. And it is that imaginary line right there that the graph cannot cross. Now, I'm going to recap how to use our calculators to make the table. Okay. So, what we're going to do. Okay, what button do I click first? Yep, okay. And if there is an equation there, you can clear it. Okay, and then you type it in just like it appears. So we will type in 2 times 1/3 to the power of X minus 1. And once you have that, what do I press? Second graph. And it gives us the table. Okay? Yes. All right. So we're going to fill in our table from -2 to 2. So what is y when x is -2? 17. When x is -1, what is y?
5.
When x is 0, y is?
1.
When x is 1, y is? -1/3. Which, what is that as a decimal?
0.33.
-0.33. Okay. What is y when x is 2? -7/9, which is -0.78. Okay. Now, you only graph the points that will fit on your graph. Does the point -2, 17 fit on our graph? No. So I won't worry about it, but I will go to -1, 5 and put a point. 0, 1, 1, -0.3, 2, -0.7. So our graph goes something like that. Okay, what is the domain of that? And the reason for that is because this graph goes to the left. So as it's going over, it's going to the left. So it eventually will get way, way out there. Way up there, though. So it goes to the left forever, and it goes to the right forever, which is where we get that. Then our range always goes from the asymptote up. So where is our asymptote? And then up forever is?
Infinity.
So -1 to infinity. And then what is our y-intercept for this one? The point 0, 1. We will always use that point right there for our y-intercept. Okay, so before I let you work on the rest of the front page, I want to go ahead and talk about the back page just a little bit. And then we will work on it for the rest of class, okay? I'd rather do all of the talking at one point than split it up. Now, for the second half of this, it is growth and decay questions, okay? There are 6 of them. You're good, go ahead. Okay? So, for these, it does not tell you if it is growth or decay, so you have to determine it, okay? We're going to look at the odds together. We're going to just set up 2 of them and talk about 3 of them, okay? So, for number 1, it says rentals in a high-rise apartment building get more expensive higher up since the views get better. The ground floor, floor zero's rent is $1,690. The rent increases 4% per floor. What is the rent on the 7th floor? Okay, so for this one, it is saying it increases. So is that growth or decay? Growth. Okay, let's find everything we need. What is our initial amount?
1,600.
All right. What is our rate?
0.04.
And then, now this one doesn't use time in years. It talks about floors. So T would be 7. Okay, this is growth. So when I set it up, it will be Y is equal to 1,690 times 1 plus. Yep. Okay, to the power of 7. Okay, that is how we set it up. And then you're going to finish that one. But we're going to go ahead and look at question 2. Okay, so for question 2, a rubber bouncy ball is dropped from a height of 192 centimeters onto a hard flat floor. After each bounce, the ball returns to a height that is 17% less than the previous maximum height. What is the maximum height reached after the 18th bounce? Okay, so is that growth or decay? Okay, where it says less than, that tells us that. Okay, so now, what is our initial amount?
192.
Okay, what is our rate? 0.17. And what is our T in this question? 18. Okay, so when we set this up, since it is decay, we will do Y is equal to 192 times what?
So 1 minus T.
To the power of 18. Okay, so we're just setting up those 2 together. You have to finish solving it, but we're not going to do that part. Then number 5, we're just going to read it and determine if it's growth or decay. Okay, so a company promises to release a new smartphone model every month. Each model's battery life will be 3% longer than the previous models. If the current model's battery life is 702 minutes, what will the latest model's battery life be 10 months from now? Is that growth or decay? Growth. Okay, so then we'll do one other one. So number 6. An architect is designing a tapered office tower where the ground floor is the largest and the floor space is reduced by 6% per floor. If the ground floor has an area of 1,460 meters squared, what is the area of the 5th floor? Growth or decay? Decay. Okay. So, I want you to take the rest of class to finish this assignment. Okay, and if you do not get it done during class, it is homework.